The Large Hadron Collider. It is near Genova in Switzerland, in Central Europe, which is Southern Europe. It's operated by CERN, and it is built in the 80s built Large Electron Positron Collider 100 meters underneath the ground. And it is 27 kilometers long. It is not a circle, it is an octagon, so of 8 sides. And it is the largest machine in the world, and it is cooled down to almost absolute zero, to 1.9 Kelvin. Now, and what happens there? There are strong magnets, strong electromagnetic fields who are kicking protons, one in that direction, the other one in that direction. They're kicking them always, if they pass it with one thing, they're kicking it on to the next part. One proton in that direction, other protons into that direction. And at 4 of these things, there are now other magnets, and they are trying to push them very small together. Protons are very, very, very small, on a very small places, so that actually, when at one curvature, hit exactly the other ones. And then they bang together. Now, and that works, and that the electric resistance of the magnets is not a break on them. They are super cooled down with helium, and also they are superconductors, these magnets. Now, and when they bang them together, then there are things to measure them. There's ATLAS and LHCb and CMS and ALICE. These are detectors. When they bang together, these protons, they are breaking up into gluons and quarks. And because we smash together, and inside of the protons, there are gluons and quarks. And when they are then detected, so first it goes on, there comes then concentric cylinders up in there. The first one is a semiconductor. So in that semiconductor, there the electrons very loosely bound. Semiconductor, you add just one electron, and it can conduct electricity. You take it away, and it does not conduct anymore. Now they come against it, and they are pushing basically at these loosely bound electrons when this semiconductor all them around, and you can see pretty much exactly where they were with gluons and quarks. And the next thing are the magnets, and they're pulling at them, and at the curvature it becomes clear how much they were pulled in, what the momentum of it was. Now, and then it is able to take that momentum at the next cylinder. So there's then at the next cylinder, there's now liquid argon and lead tungstate. And there these are stopped. Gluons and quarks are stopped in that very solid material. And when they are decreasing in speed, these gluons and quarks, they were accelerated, these protons, to 99.9999% of light speed, of speed of light. Now, when we're decelerating these quarks and gluons, then they're emitting photons. And these photons, the momentum can be now seen and calculated back to what mass they had. And the muons, they are going through it. These detectors out of lead tungstate and liquid argon, they are detected later. And the neutrinos, they are not detected at all. But it is able to calculate back what mass they had, because from the photons, how much mass the neutrinos had. No, neutrinos not. The neutrinos, they can be, if all is calculated together, what was measured, the subtraction of the neutrinos. Now the Higgs is the thing where it is calculated back. It is not, the Higgs is decaying too fast. But it is sometimes predicted to be decaying into high energy, a high energy pair of electrons, of photons, a high energy pair of photons. And it can be calculated how much Higgs would be there. Now, and if it's sometimes decaying into these high energy pair of photons, they can again measure it with a momentum and how much energy they had, with the magnets pulling at them, changing the momentum. It can be calculated back, translated back, how much energy that Higgs had, and how much mass it had. And now the Higgs has 125 gigaelectrons. And where the Higgs was discovered with the Large Hadron Collider on the 4th July 2012. And that is the Large Hadron Collider, and that is all according to the Richard Webb's particle physics book on the page 57 and 58. If you click this video away, then please tell me what the reason for it was so that I can improve. Otherwise, hi and welcome. I'm trying to learn mechanical engineering today, the Large Hadron Collider, and after we've done that, we're gonna do extensor carpi ulnar strength training that I see, and if you participate in the extensor carpi ulnar strength training, then it's at your own risk. What do they have so far? I think it is part 3 or 4. It is 27 kilometers long. It is running at almost absolute zero by minus 270 degrees Celsius, 1.9 Kelvin. It is in Switzerland. It is operated by CERN. And so you can see, it is the largest machine of the world. And it is near Genua in Switzerland. And it is 100 meters underground, built in an existing tunnel of the Large Electron-Positron Collider, which was built in the 80s. Okay, the next thing, it started to be worked on in 2008. The first attempt to switch on the LHC in September 2008 failed after 9 days when a joint connecting a pair of superconducting wires overheated, causing an explosive release of helium used as a coolant, delaying the project for over a year. Was it not switched on or not? I think it was switched on for 9 days. But what if they're saying it is only switched on after they have cooled it completely down and have it running? What if the cooling down process and the startup, was taking longer than 9 days? 2008, or when it was probably working, 2009, it was working. Now, what would be here else? 27 kilometers long. It is not a circle, it is an octagon. And there are intense electromagnetic fields, and they are kicking protons, counter-circulating under the BAM together with a speed, each one of 99.99% of the speed of light. And these magnets should not leave, lose through electrical resistance power. So electrical resistance would it be, and so they are superconducting and also supercooled. That means they are the materials which are very good conducting elements, and they are cooled down very much. And then 4 sides where magnets, we are constraining them to thinner than a hair, so that they are then on collision course. There are 4 detectors: Atlas, CMS, LHCb, and Alice. Atlas, CMS, Large Hadron Collider Beauty, and Alice. And Atlas and CMS should detect everything basically, and also the Higgs boson. When we collide the protons, they're splitting into quarks and gluons. And the detectors are in concentric cylinders. I don't know what it means, how it looks like. But the first one are semiconductors, and if such a particle passes through them, they are acting then on the electrons, then on the loosely bound electrons in the semiconductor, and it is not visible there the path of a gluon or whatever particle was. I think I hope I said right. Creating a pattern of electrical currents that allows a precise measurement of a particle's path. When there are magnets charged, so first the semiconductor, then the magnets pulling it into the side so that the movement of it is visible. The momentum. What is the difference? What is it? The magnets surrounding the detectors cause the path of a charged particle to curve with a degree of curvature representing the particle's momentum. Magnets are so semiconductor magnets pulling curve, saying the momentum. Next one is argon and tungsten. I said something wrong. I said it was tombstone. In Tombstone in Arizona, their white earth held up people who wanted to lynch someone. In the famous shooting was at the Okeko Road. Collisions with but the material is just tungstate, so it's liquid argon and lead tungstate. Argon tungstate. Maybe I'm able to say it. You have a semiconductor, the magnets, and then the liquid argon and tungstate, and the lead tungstate. And there they are stopped. So the collisions with this argon or the tungstate is very dense, and the atoms are stopped. And when they are decelerating, photons emitted. So semiconductor, magnets, and then stopped in the liquid argon. I think photons emitted stopped. The muons going through, the neutrons are not measured, the muons going through, but they are detected by the next one. Neutrinos not. Muons going through, detected by the next one. Neutrinos are not detected, but after having it all subtracted as what by neutrinos were. Then the Higgs boson. Fortunately, to infer its presence, we must measure these decay products and look for evidence that they come from Higgs. So the decay products of Higgs are foundable, not Higgs itself. Fortunately, the standard model, that is an idea of what all particles existing, but it's just a name for it. The standard model is like the period of table, the period of, what is it called? The periodic table of elements or something. In chemistry, all the 130 elements ordered up. And now here, these are the ones of particle physics, V70. Now, fortunately, the standard model predicts everything we need to know about the Higgs boson apart from its precise mass. For every possible mass, we can predict the number of Higgs particles that the LHC should produce. So we're knowing how many protons, and we know how many Higgs should be there. So it was semiconductor, magnets, then the liquid argon. The liquid argon, the momentum, the liquid argon, and tungstate. Then the fading with the photons are measured. Muons going through, stopped by the nexus, neutrinos are subtracted. Higgs can be prognosed, not measured. Decays so fast prognosed. And it should decay into a pair of high energy photons. Because momentum is conserved in particle decay, the momentum of the photons can be translated into the mass of a particle produced them. The Higgs should sometimes decay into pairs of high energy photons. Because momentum is conserved in particle decays, the momentum of the photons can be translated into the mass of a particle produced them. So the momentum of the photons is still there. It's decaying into high energy photons, and these photons their momentum is conserved. And now it can be calculated back that there was a Higgs. There are many possible sources of a photon pair, but if we concentrate on the likely looking ones, this is But if you concentrate on the likely looking ones and plot their combined momentum on an histogram, an unknown particle will make itself known as a bump, an excess of events corresponding to a particular mass. And we found it as a mass of around 125 gigaelectronvolts, and the Higgs was found in 2012. Momentum is conserved. And then it was found. The Higgs boson is also expected to decay into two Z bosons, which each decay further to two leptons. Combining the momentum of these leptons produced a peak at the same mass visible in the photon data. So combining the momentum of these leptons, the W and Z boson. The Higgs boson decays into two Zs and they into leptons. And the momentum of these leptons produced a peak at the same mass visible in the photon data. W bosons added their own strand of evidence. Combining the momentum of these leptons produced a peak at the same mass visible in the photon data. And it's also then possible to have the Higgs boson decays into two Z bosons, which are decaying further into leptons, and these leptons also have momentum, which can be calculated back to where the calculated back, not little more. W bosons, these particles decay into neutrinos, which aren't detected, so there's no definite mass bump in this case. Instead, we just see more W decays than we would expect if Higgs didn't exist. And is the W boson coming from the Higgs? And the W bosons, but that's not so much part now of a Large Hadron Collider. W decaying into neutrinos. The neutrinos are not detected, but we can detect that the W's are decaying, and that happens more as if the Higgs wouldn't exist and some Higgs was measured. Now we don't have time for a presentation, but let's look how it would be. Large Hadron Collider, 27 kilometers long, in Genova, near Genova in Switzerland, operated by CERN, started to run in 2008, 2009, and it's an octagon, and it is 100 meters deep. Something else here? It was built on a pre-existing 100-meter deep tunnel of the outer in the 80s, where this large electron-positron collider. It's an octagon. At 4 of its sides, there are magnets trying to pull that string of protons, which are on collision course, together to phenomena hairs with a head-to-head collision course. There are other magnets which are to reduce the electrical resistance, which would happening there, and there would be a break on the performance, which therefore they are supercooled and superconducted materials. And when they are conducting together, then there are different types of measurement detectors which measure it. There's ATLAS, there's CMS, ALICE, and LHCb. And they're detecting things, ATLAS and CMS. They're detecting everything. ATLAS and CMS. What are they detecting now? They should want to find the Higgs now. And the first thing, there's semiconductors. After collision, there are semiconductors. And in a semiconductor, the electrons are very loosely bound. And if the particles come in against it, these quarks and leptons, or these quarks and gluons, which have broken up when the proton have smashed apart, come against these semiconductors and leave a trace. And when it's visible, they are now they were. They are concentric cylinders, creating a pattern of electrical currents that allow a precise measurement of a particle's path. When there are magnets, they are curving it, and when the momentum is visible, cause the path of the charged particles to curve with the degree of curvature representing the particle's momentum. And as much as they are then curved by these magnets, that represents then their momentum. And then there's the liquid argon or the lead tungsten, in that they are stopped, and when they're decelerating in their speed, they are decaying into photons, and these photons can be measured in their energy, and that energy can be translated, it can be calculated back. And photons emitted as the particles decelerate can be used to measure the particle's energy, and so it can be made to know how much energy there was, and then know how it is, what particle it was. Muons are going through, but they are detected later. Neutrinos are never detected, but after having all together, subtracting it, neutrinos are the rest. Now the Higgs want to be found. And the Higgs, what is the Higgs doing? It decays. Now Higgs, what's the problem? It can be predicted how much Higgs are produced by how much proton they use on collision course. And it should come into a pair of high energy photons. So it's good that we're making the general thing here. And high energy photons. And these photons, when these high energy photons have a momentum, and the momentum can be translated back into the mass of a particle that produced them. But also, that is the first thing. So photons can be used to measure the particle's energy and so identify them. The momentum of photons can be translated into the mass of the particles that produce them. So the momentum of photons can be translated back to the mass of a particle which produced them. Mass of a particle. And then the next thing, there are many possible sources of a photon pair, but if we concentrate on the likely looking ones and plot their combining momentum on a histogram, an unknown particle will make itself known as a bump. So there's been too much mass, and there's an unknown particle, and now people know that is the Higgs with a mass of 125 gigaelectronvolts. 2012, 4th July, it was now the Higgs found. Higgs is decaying further into two Z bosons, decaying then into leptons. These leptons, their momentum can be taken. Combining the momentum of these leptons produced a peak at the same mass visible in the photon data. Yes, these leptons produce the same mass, so these 125 gigaelectronvolts. We don't have time. In the next part, we're going to go fastly over this information, read the last part, and we're trying to do the presentation from memory or what mostly about the Large Hadron Collider and how it actually works. Otherwise, whatever. Thank you very much.